Good afternoon, everyone. Are you hearing me?
Definitely, yes, sir.
All right, so as we discussed, we'll be looking at heat capacity and we just have a short activity as always here. All right, so we split the class in two sessions because of the account. Currently, it has 40 minutes. So, the 40 minutes, we hope to do most of the teaching. And then for the 20 minutes, we'll do a question. Hopefully, we'll see how that goes. But no, we have a question here. Are we have? Are we seeing the screen?
Yes, sir.
All right. So just indicate what you observe um, when we apply heat. What do you see when we apply heat? Into water. All right. So these are some water particles. So at about 1 degree Celsius, when we increase the temperature, what do you see happening with the particles?
So the particles gain more energy and they spread apart.
Right, so the particles begin to spread apart more and they move vigorously as well, right?
Yes, sir.
All right. So essentially, that's the essence of applying heat transfer. When we apply heat to a material, right, essentially we're providing the particles with energy, essentially. So as I stated, we'll be looking at heat capacity. All right, so the first objective that we want to complete today is to distinguish between specific heat capacity and heat capacity, and also to apply the relationship heat energy is equal to mass times specific heat capacity times the change in temperature. We won't be able, based on time, to look at the heat capacity of metals and liquids. So mainly we'll be focusing today on the first two objectives. All right, as you saw earlier, whenever we apply heat, we saw that the particles gained some amount of energy, right? And that energy is what leads to the particles um, vibrating more vigorously. They begin to collide with each other much more, and that results in a change in temperature. Essentially, the study of heat capacity has to do with how uh, how heat energy, the extent to which heat energy really causes a change in temperature. All right, so we have two theories, right, that has been um, going against each other for years now, but most recently we look at the kinetic theory of matter. We'll look at two, caloric theory and look at the kinetic theory of matter. All right, so the caloric theory. Now, it is believed in the caloric theory that heat is considered a fluid that flows from a hot object to a cold object when they are in contact. So the hot object gets cooler and the cold object gets hotter. And also that friction causes the buildup of small particles and more caloric. So the first red flag that we see here is that it says that heat is considered a fluid, right? That flows from a hot object to a cold object. But essentially, this is suggesting that when heat is moving from a hot object, the object that is hotter actually gets lighter, loses caloric, while the object that is colder gains mass, which is not the case, right? Whenever we, this is what is suggesting. So if it's a fluid, it's suggesting that the hot object, when it's in contact with a colder object, will lose mass, and the cold object will gain mass as a fluid, right? And we can know from any form of experiment that this is not true. All right. Also, it says that for kinetic theory, all atoms have some form of motion, right? That is the kinetic theory. All atoms will have some form of motion and they exhibit perfectly elastic collisions. So all objects, all atoms, therefore have kinetic energy. And also heat is considered the kinetic energy of moving atoms. Essentially what we're saying is that we realized in the experiment a while ago that when heat is transferred to a material, the objects, the atoms begin to vibrate much faster. And that results in a change in the kinetic energy, and that kinetic energy results in a change in temperature. All right, and the final thing here is that when mechanical work is done, the energy supplied is referred to as heat produced by friction. So we know that whenever we are moving an object, say we're pushing a box, right? That's mechanical work. That will result in a change in temperature because of, so we know that, say we go ahead and rub our hands together, right? Our hands will get warmer, right? Our hands will get warmer and that will result in a change in temperature. That change in temperature is really because of friction. All right, so if the caloric theory was true, basically we're saying that if caloric is really heat, or heat is actually a fluid based on the caloric theory, we said that when an object gets hotter, it gains caloric and therefore additional substances, but there are no evidence to prove that an object is heavier when it gets hotter. The kinetic theory was, however, proven by Brownian motion, right? When have you ever heard about Brownian motion in chemistry? Any of my chemistry friends heard about Brownian motion?
Yes.
All right. Yeah. So Brownian motion, experiment that we usually use to prove Brownian motion is when staring through a small aperture or a small hole, right? Where light is seeming through. When light goes through that, basically, we see that the large particles experience random movements, right? Essentially, like they're colliding with something. Essentially, we're saying that these large particles would smaller particles. All right, so large molecules of fluid have random motion. This proves that they are small particles with varied kinetic energies and speed. Therefore, all molecules have some form of motion and kinetic energy. Are there any questions so far?
No, sir.
All right. All right, so we'll look at heat capacity and specific heat capacity. Look at these two. All right, so heat capacity. Capacity. The word capacity means that how much an object is able to hold. Right? So essentially, we can use that. We can apply it to this phenomenon, right? So heat capacity, how much heat an object is able to hold, or we could switch it and say that how much heat we have to apply to an object to basically get it to change temperature. That's the basic of heat capacity. So when we were doing the experiment, we saw that there was a heat source. That heat source was applying heat energy to the water molecules in the container. We saw that, right? Now we want to measure how much heat is it supplying that particular sample of water. That's what heat capacity is saying. So it's really, sorry, a mistake here. Right. So it's really when we apply heat to an object, right? If we apply heat to different types of object, they may require different amount of heat to get that temperature change. So if we apply heat to a metal, right, versus let's say that, let's say we have a less dense metal and we have a more dense metal. The less dense metal may, the more dense metal may require more heat to get a temperature change, right? Versus a less dense metal. To get a temperature change, you have to apply more heat to the more dense metal to get that 1 degree Celsius. So the heat capacity of an object is the amount of heat energy that is required to change its temperature by 1 Kelvin or 1 degree Celsius. All right. No, we did not. We did this in the gas law exercise, converting degree Celsius to Kelvin. Right. So you can, I think notes are still in the group. You can go back to that to do practice of converting Kelvin to degree Celsius. But what you must note is that 1 Kelvin, the magnitude of 1 Kelvin is the same magnitude for 1 degree Celsius. That's what we must note. All right. Okay, so heat capacity. The formula for heat capacity is heat energy over temperature rise. All right. So heat capacity is heat energy over temperature rise. And that is denoted by the big C. Big C. Now, specific heat capacity slightly slightly different, because now we're considering a sample of that particular object. So heat capacity is for the object in general, while specific heat capacity is really looking at the sample of that particular object. Now, the heat capacity, specific heat capacity of an object is the amount of energy that is required to raise 1 kilogram by 1 Kelvin, or we could also say 1 degree Celsius. So in this case, we're now seeing where mass is involved. right? We're now seeing how mass is involved in this case. So our formula is specific heat capacity is equal to heat energy divided by mass times temperature. All right. Now let's break this down. So we're saying that C is equal to heat energy divided by mass times temperature. All right. Now what is it suggesting? We see that C, or heat specific capacity, is directly proportional to the amount of heat energy, right? And also it is inversely proportional to the temperature, right? So essentially specific capacity, if we'd have to apply, if the specific capacity increases, for example, if we have a much more dense material, right, we'd have to have more heat energy to get the temperature change that we want, right? So they are directly proportional, directly related, right? Also, if we have the same amount of heat energy, if we have a constant heat energy supplied, but we change the materials, right? But we have, say we change the materials and we get one with a lower specific heat capacity, then the temperature change will also will basically go up. What we mean by that, say we have a metal, we have a less dense metal. Let's say that this one is less dense. And this one is more dense. They are of the same volume and the same mass. This one, the more dense, has a higher specific heat capacity, right? It will require more heat, right, to get that same temperature change. Now, if we want to look at how temperature change affect the specific capacity, how they're related, we could apply 500 joules to both of them, just for investigation. We could apply 500 joules to the less dense one and the more dense one. And essentially, we would realize that that they're both have some form of temperature change, but which one will have a greater temperature change? All right, so let's say that we apply 500 joules of heat energy. This one has a lower specific heat capacity. This one has a higher specific capacity, just for argument's sake, right? And we apply 500 joules to both of them. Which one will have a greater temperature change? Anyone? Or you want to make a suggestion, or I don't want to say guess. Which one do you think? All right, so more dense. All right. Honors. Okay. All right. So it would be the less dense, right? Because the less dense would require less amount of energy to get the same temperature change, right? So the less dense, if we apply 500 to the less dense and 500 to the more dense, right? The less dense will you will get you will get more energy change for that one. All right. All right, so let's look at the units for specific heat capacity. All right, could someone remind me of the units for joules for energy? I already gave it on. So joules, now what would be the unit for mass? So the unit for mass would be kilogram. All right, thank you. Thank you, Devon. Thank you, Violet. And then it really depends on the question. Will either give you in degrees Celsius or degree Kelvin, right? But it can be either degree Kelvin or degree Celsius. So let's place back degree Kelvin. They are of the same magnitude. All right, they are both the same magnitude. All right, so since these are in the denominator, to write them to make it look more uniform, because essentially when we write in our units, we don't really put them in a fraction form. We usually have joules. This represents per kilogram per Kelvin. Okay, let's do an example question. Okay. So the specific heat capacity of solid copper metal is 0.385 joules per gram per Kelvin. Right. Slide down. Let's do it in joules per kilogram first, and then we do that. So we said that our formula for specific capacity is C equal mass, sorry, equal heat energy over mass times temperature change. All right. So we want to find our heat energy, right? So we'd have to solve for heat energy. Place it on one side of the equation, and then we multiply both sides by mass and temperature. So specific capacity is for the metal is 14,630 times our mass. Mass of the block is 2.12. The change in temperature, no, this is very important. The change in temperature, right, is 99 degrees, 99.9 degrees minus 25 degrees. All right. All right, could someone get their calculators and work this out for me? How much do you get?
74.9.
78.9?
74.
74? I didn't hear.
Yes, sir. 74.9.
Okay, okay. Just want to make sure. All right. Thank you as well, Devon. All right, so it is 14,630 times 2.2 times 74.9. And how much do we get? All right, could someone confirm? Okay, great. So that is the amount of heat energy to get the copper from 25 degrees Celsius to 99.9. Are there any questions?
No, sir.
All right, so we'll pause here. As you can see, the time will go out in 5 minutes. So we'll go out and then we join back to do the question that I posted in the chat. All right. So I'll end here and then we join back to the question.